Today we're going to talk about resonance and resonance structures. We're going to start by considering the following anion. This is the nitrate anion. And we're going to find the Lewis structure for this. We're going to start by finding the total number of valence electrons in the ion. And because this is an anion, we're going to add an extra electron. We see that nitrogen has 5 valence electrons and oxygen has 6, but we have 3 of those. So we have 18 electrons from the oxygen, and then we have to add 1 more for the -1 charge on this ion. So the total number of electrons we need to have in our Lewis structure is 24. Now let's try to figure out which atom is going to be the central atom, and this is going to be the one that's the least electronegative. So this will be nitrogen, which is less electronegative than oxygen. So we're going to go ahead and put it in the center and put our oxygens around it. Now the next thing we need to do is connect each atom to the central atom with a single bond. We'll do it like this. And then we're going to subtract the electrons we used up from the total number that we calculated before. So we have 24 electrons in this structure, and if we subtract 6, we have 18 left. Now we're going to take these 18 and we're going to distribute them as lone pairs on the terminal atoms, and that means the atoms on the outside. And then we're going to subtract these electrons from the total electrons. So we had 18, and we're going to subtract 18, so we don't have any extra electrons left to add. If we did, we would put them on the central atom, but we don't need to do that because we have none left. Does everyone have a full octet? We see that all of the oxygens do. Each oxygen in the structure has 6 lone pair electrons, and they share 2 electrons with nitrogen, and that's going to bring them up to 8. However, if we take a look at the nitrogen, we notice that it only sees 6 electrons, 2 electrons in each of the bonds, and we can't have this. Per our Lewis structure rules, we're going to make a double bond somewhere. If we do that, that is going to make sure that nitrogen has a full octet. Where do we put this? We could put our double bond here, or we could put it over here, or we could put it over here. And all of these would be acceptable. So we have 3 possible valid Lewis structures. We call this resonance when you have more than one possible Lewis structure for your molecule or your ion. We use arrows to illustrate resonance, like this, but you have to remember that these different structures are not really switching back and forth. These arrows are just symbols telling us that there are 3 possible structures. What's really going on? Well, when they do experiments, they see that each of these bonds, each of the bonds in this nitrate ion actually has equal length and equal strength and equal energy. In fact, all 3 bonds behave like a hybrid between a single and a double bond. And sometimes people want to represent it like this, where each oxygen forms a single bond with the nitrogen as well as a partial bond. We say that electrons are delocalized across all the bonds. These electrons aren't really shared like we're used to in our little covalent compound diagrams. They're shared over all of the atoms and not just 2 of them. Here's another example where we have 3 different resonance structures. Remember, these aren't flipping back and forth. Our real structure is actually a hybrid of all 3 of these. And this is what you would see. The bonds aren't really double bonds and they're not really single bonds. They're somewhere in between. And here are a few more examples. On the left-hand side, you see the resonance structures, and these are indicated by that double-headed arrow. But on the right, you see what's really going on. These electrons are delocalized, and the bonds aren't single, they aren't double, they're somewhere in between. Here's another way to illustrate this. A rhinoceros is not a unicorn, and it's not a dragon, but it does have features of each. It is an average, and that's what we're looking at with resonance structures. Sometimes we're asked to calculate the bond order. Now, bond order, it helps us describe what we're dealing with in these structures. Are we dealing with single bonds, double bonds, something in between? And we've already seen this in an earlier topic. Our single bonds have a bond order of 1, our double bonds have a bond order of 2, and our triple bonds have a bond order of 3. When you have resonance structures, in order to calculate the bond order, you look at the number of bonds that are coming off of the reference atoms. We'll talk about what this is in a moment. And you divide that by the number of bond groups between the individual atoms. Now let's see what this means. In this particular resonance structure, we have 4 different bonds. We have 2 single bonds and 1 double bond. That means 4 bonds. But we have 3 bond groups. The nitrogen is bonded to one of 3 different oxygens, so 3 bond groups, and when we divide these, we get 1.33 bonds, so that is our bond order. Let's do another example. Each of these structures has 3 bonds, 1 single bond, and a double bond. There are 2 bonds in the double bond. That's 3 bonds total. However, there are 2 bond groups. There are 2 oxygens that are bonded to the nitrogen. If we divide 3 by 2, we get 1.5 bonds, and that is our bond order. It's important to remember that in resonance structures, only the electrons are rearranged. The atoms are not rearranged. So when we were doing formal charge, we were looking at things like this. These are not resonance structures. You can see that every structure has a different central atom. These are not resonance structures, but these are. The atoms are in the same places in all 3 possible resonance structures. However, the only thing that varies is the position of that double bond. So let's summarize. Sometimes we're able to draw more than one Lewis structure for the same molecule and still have them follow the octet rule. This is called resonance, and we use these arrows to indicate that a particular structure is in resonance. But remember, these structures are not really switching back and forth. In the lab, we see that the true structure is actually a hybrid between the different resonance structures. We can calculate bond order by taking the number of bonds that are coming off the reference atom, often the atom in the center, and we're going to divide that by the number of bond groups between the individual atoms. For example, here we have 3 resonance structures. Each of them has 4 bonds and 3 bond groups. When we divide 4 by 3, we get 1.33.